Hello. Hi to everyone. Welcome to the Unit 2, chapter number 3, time constant. So, in this particular chapter, in your examination, you may expect one question. Okay. So, within one video, I am going to cover the complete chapter, complete topics in this particular chapter. Okay. So, let us start our discussion. This is a small chapter. Okay, right. Rise and fall in currents in pure resistance. What are the topics I am taking from your syllabus only directly? Okay, so rise and fall of current in pure resistance. So let us look at here. You know, 12 volts battery is connected to 6 ohms resistance. So initially I'm switch is open circuited. There is no current flowing. My question here, whenever I'm switch on the power supply, so at the instant of for ideal case, at the time t is equal to 0, at the instant time is equal to 0 or 0 plus, whenever switching the power supply, the current value I is equal to V by R. That is a V by R, that is a 2 amperes. What is the current now? It is a 2 amperes, from the Ohm's law. But the what is important thing you need to remember, in case I'm opening the switch, for example, when I'm opening the switch, what about the current at the instant? Whenever I open the switch, at the instantly it is a 0 amperes. There is no time delay. So finally my conclusion here, in rise and fall time of pure resistor, rise and fall time of pure resistor is 0. There is no time delay in case of rising current as well as falling current. Instantly it is a rising current, see here, instantly it is rising current, instantly it is falling current. Then you will get the doubt, what is the reason behind instantly rising current and instantly falling current? The reason behind, in case of capacitor, in case of inductor, it store the energy in the form of magnetic field. In case of capacitor, it store the energy in the form of electrostatic field, electrostatic energy. But in the case of resistor, it won't store any energy. That's why at the instant we switch on the power supply, it allows the current. At the instant, it allows the current instantly. Whenever you switch off the power supply, the current will be disappear. That is the reason why it can't store. Finally, you should conclusion here, it won't store any energy. It is a any energy. That is the reason why the resistance, fall and rise of currents in resistance will be instant. Okay, so that is about the first. After that, we are moving to the second one, time constant. So time constant of a RL circuit, very important. So in the time constant of RL circuit is lambda, sometime tau or lambda. It going to be mentioned lambda. This is a lambda symbol. L by R. It is a seconds. So what is the time constant of RL circuit? L by R, seconds. So here lambda is a symbol for time constant, but you need to remember some theoretical concept related to the time constant. Then you will get the complete idea about the time constant of RL circuit. First I will tell you, whenever I am switch on the power supply, okay, when I am switch on the power supply, what will happen at the instant you switch on the power supply, like in a resistor, it wants the current instantaneously increases, but the current will be increases from 0. Initially we are switch on the power supply also, sometimes the current will be 0. After that, what will happen, inductor going to be charging, the current will be gradually increases. Whenever it reach to the 5 time constants, inductor going to be reach the maximum current, that is a 1 ampere. So now I'm going to give the definition of time constant. Time constant is defined as, okay, I will give the time constant definition, then we will get the complete idea about it. So first, it is defined as time constant, defined as time during which inductor or capacitor, we can inductor or capacitor raise in voltage or current. In case of inductor it is a current, in case of capacitor it is a voltage. 63% of its final steady state value, that is called as a time constant. Got my point? Finally, what is the time constant? Whenever you are giving the switch on the power supply, the inductor is trying to reach the current up to the 63%, that means 0.63%, 63 amperes of the maximum current. Here maximum current is 1 ampere. What is the 63%? 0.63 amperes. Then you will get the time constant. Okay, in this particular case time constant tau is equal to 0.1 ampere. So when we reach the maximum current, in general 5 time constant, that's why it is a 5 time, 5 into 0.1 into 5, that is a 0.5 time constants. So at the 0.5 we'll get the maximum current. After that it going to be decreases. So everyone got the idea what is mean by time constant? The time constant means whenever the current or voltage will be raised to 63% of final steady state value, then it is called as a time constant. How much time it will take, how much time constants it will take any circuit to reach the maximum value? 5 time constants. Very, very important. At the 5 time constant, it reached to the steady state value, any circuit. So that's what your time constant. I am going to explain the time constant in the another manner, that is a decay, the rising up to 63%. What is a fall case, decreasing case, the time constant? So let us see. Another definition I'm going to give to you. It is defined as time constant in another way, in the decaying case. It is defined as time during the capacitor or inductor voltage or current fall 37% of its initial maximum value. That is about the time constant in case of decaying case. Let us explain here. Here 1 ampere is the initial value for the switch is open. Okay, whenever switch is open, so see here, look at this particular diagram. So time constant definition, whenever switch is open, at the time of switch is open, what is the current you got at the 5 time constant? 1 ampere. That means what is the initial current in the inductor? That is a 1 ampere. So that's what here it is defined as a time during the capacitor inductor voltage fall in rise voltage or current fall to 33% of initial value. 33% of initial value, that is called it as a time constant. So 33% is nothing but a 1 ampere, 33%, 0.37 amperes. In this particular case, we will get the time constant of again 0.1 time constant. Whenever it is decays completely, 5 time constants again. Okay, 0.1 into 5, there is a 0.5. Then it will completely, it is decaying to 0. Okay, this is about the ideal case I am going to discuss about this particular concept, time constant of RL circuit. I hope that everyone is clear about the time constant of RL circuit, right? So let us look at the next topic, circuit conditions. For RL series circuit, what are the conditions we have? So in this particular case, I am going to discuss about the two cases. The first case, whenever switch is closed to at one position, switch is closed to second position. So whenever switch is closed to first position, so what will happen? At initially, it is offers zero current. because of inductor won't allows a sudden change in current. It is a zero current, it is offers. Whenever you are increases the raising current gradually, so whenever it reaches to the time constant of 5 time constant, whenever reach to the 5 time constants, so the time will be 5 time constants, then inductor reach to the maximum value, steady state value. At a steady state, everyone see, at a steady state, inductor act as a short circuit. You know that at a steady state condition, inductor act as a short circuit. At a transient condition, inductor act as a open circuit. Initially, whenever switch on the closed at t is equal to 0, inductor won't allows any current. The value is equal to 0. Whenever it reaches to the 5 time constant steady state value, inductor act as a short circuit. Only what is a present? Only present is V, what we are applying, that is a voltage across a resistor. V is equal to VR. Total entire short circuit voltage across the capacitor will be 0 in this particular case. Clear? So finally, in this particular, in the case of RL, in the case of RL circuit, I will provide a formula directly to you. Whenever raising current, that means charging, whenever current raise, the formula will be, so everyone note down this particular formula, current raise formula. So current raise formula, I is equal to Im into 1 minus e to the power of t by lambda. Time constant of RL circuit, lambda is equal to L by R. And then Im is a maximum current. Whenever the resist voltage, that is the inductor voltage is equal to 0, that is I maximum is equal to V by R. Okay, that's what these two formulas, that they ask any question in the examination, you can attempt. I is equal to Im e to the power of minus t by tau, current raise. As well as I will give the another formula, current decay. Okay, current decay. In the current decay, I is equal to, for example, IR, ID, current decay. So current decay is equal to Im into e to the power of minus t by tau. Okay, these are the current in the raise. This is a formula for current in fall case. Okay, then I will ask the one question to you, and the question will be, for example, R is equal to 120 ohms and L is equal to 24 Henry. So what about the lambda value, time constant? Time constant tau or lambda is equal to L by R. What is the L 120? What is the R 24? That will be equivalent to 0.2 L by R. Sorry, 24 by 120. That will be equivalent to 0.2 seconds. Okay, that's what your calculation of time constant L by R. Then we are moving to the next topic, that is a inductive kick. So in the syllabus it is mentioned what is mean by inductive kick. See, initially what I am doing, that switch is a closed, right? Whenever switches are closed, what will happen? Through the resistance, the inductor going to be energized. Whenever inductor going to be energized, the energy across the inductor is equal to of Li square of the current. So whenever it is energized, so now I am connected to neon lamp. What exactly the neon lamp offers? Very high resistance. So whenever it reaches to the maximum value, that is a 5 time constant, time is reached to the 5 time constant, inductor reached to the maximum value. What is the maximum value reached to the inductor at 5 time constant? I is equal to V by R. At the 5 time constant, inductor act as a short circuit, right? That means that maximum current will be V by R, that is a 10 by 100, that is a 0.1 amperes. Whenever it is reached to the 0.1 amperes at 5 time constant 5 tau, So inductor completely charging, the neon lamp tries to what we call lighting the lamp. Okay, light will be emitted. So whenever I disconnect this particular lamp, suddenly what will happen? Already inductor stores the energy of Li square, but is trying to discharge this particular energy what is stored. There is no path. Okay, there is no path to try to discharge the current, but inductor always it is present, it opposes a sudden change in current. Or whenever you disconnect it directly through the circuit, we switch off the switch, open in the switch, what will happen? Inductor is going to be burned because the inner insulation is trying to discharge. The more currents will be there because of more voltages in the terms of, for example, in the picture tube, 2 kilowatt 2 kV 2000 kV also present in the picture tube. This is the inductive kick. So this type, for example, one person is working here in the nearby the inductor but particular circuit, that person touch the particular inductor, what will happen? That person going to be maybe severe impact on that particular person, because very high voltage around 2 kilo ohm or 3 kilo ohm, that is a 2000 ohm, sorry, 2000 volt, 2 kilovolt or 3 kilovolt, that much of voltage withstand here. That's why what we do, this particular inductive kick, by short circuit some resistance across the inductor, we are going to discharge everything, then it is a safely we can particular person working safely on the inductor or some other picture tube, what we are explained, what I gave the example of TV picture tube, that is an inductive kick. So everyone is clear about the inductive kick. What is mean by inductive kick? Finally, whenever you disconnect suddenly from the inductor to the circuit, inductor is trying to discharge their what with their energy, but there is no path to discharge. Very high voltage it is offered. That's why it is a dangerous to the person they're working near, and this may cause of the inductor going to be damaged also. Okay, next we are moving to the time constant of RC circuit. The time constant of RC circuit is lambda is equal to RC. Time constant of RC circuit, lambda is equal to RC. That is a time constant. Whenever you maintain more resistance, you will get the more time constant. Whenever you maintain the more capacitance, you will get the more time constant. That is directly proportional. So here the definition of time constant is the same as previous definition. So the definition is, it is a time during which charging, time during which charging current raising 63% of its final value, as well as falling its initial value of 33%, that is a time constant already explained there. So from that, I'm going to explain the charging and discharging about the capacitor. Okay, look at here, charging and discharging. So whenever switch is closed here, initially, at a transient period, inductor, capacitor act as a short circuit. Very, very clear. At t is equal to 0, we have switch on the power supply at the position of 1. The capacitor act as a short circuited. Whenever it is a short circuited initially, the current value at a transient period is equal to V by R. So V divided by R only. So that means that at the time of starting, what about the current here? Maximum. Yes, here. At the time of starting, the current value is a maximum. That is a IM. Whenever switch is moved to the second position, the capacitor is gradually discharges up to 5 time constant is reached to the 0. Whenever the current will be maximum, what about the voltage across the capacitor is a voltage across the capacitor. So this is a VC across the capacitor. So the voltage across the capacitor, initially it is current is a maximum, it is starting from 0. So it is starting from 0. At a time constant of lambda, its value will be reached to the 63% of its final value. So whenever it is reached to the 5 time constant, capacitor reached to the maximum voltage, what about the current flowing through the capacitor is 0. That means that at t is equal to infinity steady state condition, capacitor acts as a open switch. So capacitor acts as an open switch. It stores some energy in the form of electrostatic field, and then that value when I was moving to the switch number 2, that value is the initial value for the second phase. So that's why, so whenever it is second position, capacitor is slowly discharges, its voltage is decreasing, and then current value is starting from negative to, it is going to, because of it initially it is a polarity, the polarities of this particular capacitor change, the current direction is also changed, capacitor. But inductor, the current direction is continuous same as, but it won't, it opposes a sudden change in current. But in the capacitor, current direction going to be changed. But this much of depth is not required for you, for your understanding purpose I am explaining. So everyone is clear. Finally, what we remember in this particular case, time constant of RC circuit, lambda is equal to RC. This is about the explanation of capacitor charging and discharging. Okay. Now I will ask the one question related to the time constant in the case of capacitors. Okay. So what is the, for example, the resistance value R is equal to 2 mega ohm and capacitance is equal to 0.02 microfarad. What is the time constant? The time constant lambda is equal to RC. So 2 into 10 power 6 into 0.02 into 10 power minus 6. So these two are get cancelled. You will get the value of time constant tau is equal to 0.02 seconds. 0.04 seconds. That's what time constant calculations. Next we are moving to the decreasing time of capacitance. Okay, decreasing time of capacitance. So in this particular case, the decreasing time of capacitance is related to the phi time constant of its phi time constants. So for example, switch tau, I will take this particular circuit and then I will explain the decreasing time constant. Whenever I connected the switch 1, whenever it reached to the phi time constants, whatever the current it is offers, I is equal to V by R, 10 by 2K. That is the value is of 5 milliamperes. Whenever the current reaches to the 5 milliamperes, the phi time constant, I switch on the power supply. I switched moving to the lamp bulb. It is connected directly. So what will happen? The bulb will be glow. The bulb will be glow up to the value fall to the 37% of its final value. Okay, that value. So here 5 milliamperes is flowing through the bulb. So up to that, the capacitor going to be discharged. Again you are switch on the power supply to this particular one. Again it is charging. Again is moving to the point number 2. Again it is discharging through the bulb. So this is the time constant, decreasing time constant. In this particular way I am going to calculate in the phi time constant value. So next we are moving to the flasher type. Flasher is nothing but a, whenever you switch on the power supply, capacitor is trying to charge up to phi time constant. After that, whenever it reaches to the phi time constant, neon lamp will be glow. After neon lamp will be glow, what I am doing, that particular switch is open circuited. Capacitor is connected to the neon lamp. Whenever capacitor is connected to the neon lamp, it will be working as a bulb up to the capacitor value fall in time reached to the minimum value. Whenever it reaches to the minimum value, light will be off state. Again we are switch on the power supply S1. Again the lamp will be, again the capacitor will be charging. Once it is charging, we are supply to the bulb, that particular neon lamp. This thing is happened, whenever neon lamp I disconnected now. So whenever I neon lamp I disconnected, this particular switch is open, then I connected 1 mega ohm and then capacitor across that, then is trying to discharge. Otherwise flasher is nothing but a spark will be occur whenever we are whenever you are directly short circuited the both the terminals of the capacitor. This is about the flasher. That is enough for the explanation about the flasher. Then we are moving to the pulse response of RC circuit. Pulse response of RC circuit, we'll see. So the pulse response of RC circuit, in this particular diagram, this is a pulse I am provided to the circuit. So in this particular case, the pulse response, for example, the pulse response is it is up to the 5 time constraints. So then it is a no problem, because see here the capacitor values increases up to 5 time constant, that is a 63 100 volt. 5 time constant is a 63%. From its value time constant. After that it's going to be decreases and then increases. That this is a value of capacitor for the 100 volt. Again this is a time constant tau, 63 volts only. Whenever the decreasing the capacitor value up to 37% of its final value, that is also one time constant. So this is about the voltage across the capacitor in the decreasing. So this is the voltage across. Again this is the voltage across the resistor. It is a voltage across the resistor increases the current instantaneously. That's why it is a current or voltage is a maximum. And then it is a, this is a fall, same as, you know, this is increasing and decreasing. So that means that whenever current is present, current will be available at the resistor. If current is zero, current will be zero in the resistor instantaneously. This is the waveforms about pulse response of RC circuit. So now we are taking the effect of long and short time constants. Effect of long and short time constant. What is mean by long time constant? What is mean by short time constant? So long time constant means whenever the pulse is available up to 5 time constants, then it is called as a long time constant. Okay. So short time constant means whenever the time constant less than the 5 lambda, 5 time constants, then it is called as a short time constant. That means that pulse is available up to 5 time constants, it is called as a long time constant. Whenever pulse is not available up to 5 time constant, that is a short time constant. So look at here, in this particular case 100 volt is given up to time constant 0.02. It is available. It is like a oscillator, sawtooth waveform. This is about the voltage. This is about the current across the particular RC circuit. Okay, this is the voltage across the RC circuit. These are the waveforms. Okay, that means that square voltage waveform applied to short interval of time. Short pulses we are connected. This is the waveform we are represented. That means that the capacitor is not the completely charging up to 5 time constant. This is the waveform. For example, if I am connected square voltage waveform applied to long time constant, what will happen here? Whenever you are applying long time constant up to 0.05, okay, pulse, the pulse width, so the voltage up to reach it to the 0.5, that is a maximum. So whenever it reaches to the maximum up to 5 time constants, right? Yes, once it is a completely charging, again discharge up to time constant of 1 time constant. So again it is discharge, again 5 time constant, again charging. That means that whenever using long pulses, the capacitor always some charge will be present, increasing or decreasing. It is not to the reach to the zero. So that's what here the current and the voltage values of the waveforms whenever long period. This is a resistor voltage waveform. So I hope that everyone is clear about the time constant RC and RL. So this is about the chapter number 3, time constant, in the unit 2. So this is enough. You may expect the one question from time constants. What I gave the formulas to you: lambda is equal to time constant of RL circuit is equal to L by R. Time constant of RC circuit is equal to RC. RC circuit is equal to RC. Those two you may expect in the examination. And then thank you.